Okay, so we're talking about the dot product. And in contrast to vector operations that we were adding or multiplying and that resulted in a vector, this time we're taking two vectors and we're going to combine them to obtain a real number or a scalar. So we were looking at the following. Remember that the dot product is equal, multiply the first two terms in the two given vectors for A and B, and we end up with a scalar. Okay, so here we have an alternative formula for the dot product. And this formula comes from something that we were talking about before, how we find the angle between two given vectors. So here, if I isolate the dot product, I move the magnitudes over to the left side of the equation, I end up with this particular formula. So an alternative formula for the dot product is if we have the magnitude of the first vector, the magnitude of the second vector, multiply it to the included angle, then we're going to end up with the dot product. So here's the diagram. Here's vector v, w, and the angle between these two vectors, and we're going to get that scalar value for the dot product in an alternative fashion. Or if we're looking for the angle between the two vectors, we're going to take the dot product divided by the magnitudes of each, and then in our calculators we're going to find our cosine of that. Okay, so just to recap, it says find the angle theta between the two given vectors. So we're interested in this particular angle, and let's go ahead and find that. So I'm interested in the angle between vector v and w. So cosine of theta is equal to the dot product over the magnitude. Okay, so now let's find the dot product. Alright, so we have vector v, vector w, and remember to find the dot product, we're going to take a1 times a2 plus b1 times b2. And so we're going to get negative 6 for the first term, plus negative 10. So here I get negative 6, here I get negative 10, and that equals negative 16. And then I'm going to take the magnitude of vector v. So remember, another formula that we learned was if I take the dot product and then I just square root it, then that's equivalent to, so I should say magnitude for vector v is the square root of a squared plus b squared. When I square it, it's going to be positive, so it's going to be 4 plus 4 is equal to the square root of 8, or 2 radical 2. Now we're going to find vector w, the magnitude of that. 9 plus 25 equals radical 34. So for magnitude of vector v, we get square root of 8, square root of 34. Multiply those two together, we get square root 272. So in my calculator, I'm interested in arc cosine negative 16 over radical 272, and that is approximately 165.96 degrees. So the angle between these two vectors is 165.96 degrees. And we also talked about parallel and orthogonal vectors, but more specifically, when two vectors are parallel, the angle between them is going to be 0 or 180 degrees. And two vectors are orthogonal if the angle between them is 90 degrees and their dot product specifically is 0. Okay, so here's a diagram that shows what two parallel vectors would look like, with an angle between them being 0 degrees on the left or 180 degrees on the right. So this just recaps: the angle between two orthogonal vectors is 90 degrees, however their dot product is 0. Okay, so are the following two vectors orthogonal? So here I would just take the dot product because we're only determining if it's orthogonal. If I was determining whether they were parallel, I would go ahead and finish the formula for the angle between the two vectors. So 2 times 6 plus negative 4 times 3. So 12 plus negative 12 equals 0. I don't have to show any additional work because the dot product is 0. If I would have ended up with a value, I would go ahead and find, remember, cosine of theta is equal to the dot product over the magnitude. And then if I end up with the angle between the vectors being 0 degrees or 180, then I know that the two vectors are parallel. Okay, so now we're going to project a vector onto another vector. So before, in our previous section, we were taking two forces, putting them, adding them together, and then describing or finding the resultant vector, finding the magnitude and direction of that particular force. And now we're going to decompose it. We're going to break it apart. We're going to think of having the resultant vector as the given and breaking it apart into force 1 and force 2. So here is a particular example. Okay, so this just recaps a little bit about what I was saying. So we're going to reverse the process by expressing a vector as the sum of two orthogonal vectors. So we're interested in that the force that was applied and in the particular direction. So for instance, if we look at the diagram here on the left, the force due to gravity is this F here. It's pulling straight down on the boat. Part of this force, F1, is pushing the boat down the ramp. Another part of this force, F2, is pressing the boat against the ramp at a right angle to the incline. So these two forces, F1 and F2, are called the vector components of F. And notice that F is equal to F1 plus F2. So a method for finding F1 and F2 involves projecting a vector onto another. So we're finding, we have the result and we have F. We're going to break it apart so that we can find F1 and F2. Okay? So how is the vector projection of V onto W formed? So I want you to draw the line segment from the terminal point of V that forms a right angle with the line through W. So it would look something like this. So we're going to drop an altitude here, create a right angle, and extend this in this direction. So this complete red line that I just drew here is the projection of V onto W. Specifically, the projection of V onto W lies on the line through W and is parallel to vector V, parallel to vector W. So how do we solve for the projection of a vector onto another? We're going to use the following formula. The projection of V onto W, we're going to find the magnitude of each, and then we're going to find the magnitude of W squared, multiply it by vector W because that's the one we're projecting onto, and we're going to result with a vector. So how to find the vector components? After we find the projection of vector V onto W, then the next component, basically what we're going to do is subtract the projection from the given vector, and we're going to obtain V2, or the second force we were looking for. So doing that is called the decomposition of V into V1 and V2. So here's an example. If vector V is equal to 2i plus 4j and W is negative 2i plus 6j, find the vector projection of V onto W. So the first thing I'm going to do is the following. Alright, so here's our given vectors. And we're going to project V onto W. So what we want to do is we want to find the dot product first. So 2 times negative 2 plus 4 times 6 over the magnitude of vector W squared. So I'm only interested in basically the dot product. So negative 2 times negative 2 plus 6 times 6. Okay, and then when we simplify it, here I get negative 4. Here I get positive 24, so in the numerator I'm going to get 20. Here I'm going to get 4 plus 36, I'm going to get 40, or half. And then I'm going to take that scalar, and our formula says to multiply it by vector W. So we're going to take a half of negative 2I plus 6j is equal to negative I plus 3j. So this is equal to component 1, or the projection of V into W. Now let's say, for instance, that we were actually looking for component 2 as well. So in this scenario, we're still using the same vectors, V equals 2I plus 4j, and W equals negative 2I plus 6j, but we're interested in component 2. So remember, vector 1 was equal to the projection of V onto W, which we said was negative I plus 3j. And now we're going to find component 2, and that's equal to the difference between the given vector and V1 that we found. So the given vector was 2I plus 4j. We're going to subtract the vector we just found, so minus, and it's negative I plus 3j, so that means I'm going to have to distribute. I'm going to get positive I minus 3j, so that's 3I plus j. This is component 2. All right, so let's talk about work, and this is an application of the dot product. So the definition of work, specifically the work done by a force F moving an object from A to B, is equal to the force times the distance from A to B. So the magnitude of the force times the distance from A to B. If a constant force F is applied to an object, moving it from point A to point B in the direction of the force, then that's the work that we're specifically talking about. Specifically, work is often measured in foot-pounds or in Newton meters. And it's important to note that when we're pushing something, it's different than when we're pulling something. Okay? The force of pulling, for instance, a wagon, okay, is not applied along the line of the wagon's motion. So in this case, the dot product is used to determine the work done by the force. So here's an example of that. So the work done by a force F moving to an object from A to B, remember that's the magnitude of that force in the direction. When we're pulling, we're going to use the dot product. So we're going to take the magnitude of the force, the magnitude of the distance over which a constant force is applied, and we're going to take theta, the angle between the force and the direction of motion. So in this instance, work done, a person pulls a sled with her dog on it along level ground by exerting a force of 50 pounds on a rope that makes an angle of 30 degrees with the horizontal. How much work is done pulling the sled 100 feet? So the magnitude of the force in this example is 50 pounds. The distance over which the constant force is applied is 100 feet. And we're going to take cosine of 30 degrees. And cosine of 30 degrees is square root of 3 over 2. So after we multiply all that and simplify it, our answer is approximately 2,165 foot-pounds.